You got your surface charge density. Once you go to 2D, that means this is going to be the Coulomb per meter square. We did the line, right? So you just want to do now a surface. Let's imagine a surface, yeah? Now the charge is not just on the line, but it's distributed on the surface. That means I need to know what is the electric field due to the small little area ds, then the electric field due to this small little area ds, and so on, and do the double integration there. So for that, then I need to define what is called as the surface charge density, which is the charge per unit area, instead of charge per unit length. Notice that this is a surface, rho s. S stands for the surface. Rho L, L was for the line. So surface is Coulomb per meter square. So the total charge is going to be rho s times ds. Similarly, just like how you did for this case, the total Q was rho L dl. Now you're doing the exact same thing, that if I were to have this small little dq here in this area, this dq is going to be rho s ds based on this. dq is rho s ds. Just like earlier, how I had dq equal to rho L dl. It's exactly the same thing. So that small little electric field due to the small little charge is going to be rho s ds over r square, where r is the distance between the source and the destination, over 1 over 4 pi epsilon naught in the direction of r hat. It's exactly the same Coulomb's law. So once I know what is the small little electric field due to the small little charge, I'm going to move on to this dq, this dq, this dq, this dq, so on. So I'm going to integrate it over the surface and end up getting a surface integral over the surface dE, where this ds, rho s ds becomes this term here, the rho s ds here. So similarly, the 3D, it's going to be the charge instead of a surface, I'm going to have a volume law. And in this volume, I can have a small little volume dV. The charge per unit volume, becomes my volume charge density, where V stands for, rho V stands for the volume. Instead of a surface, it's volume. And it's in Coulomb per meter cube. This is like mass density, mass per unit volume. Similarly, here it's charge per unit volume. So this dq is going to be rho v dv. The total charge is going to be completely over the entire volume. What's the charge density? It's like mass times volume is the, the mass density times the volume is the mass, right? Similar to that, density times volume is the mass. So again, we find this small little dq. The small little dq is rho v dv because of this guy here. Because of that rho v dv, what's that small little electric field at that point? Again, by Coulomb's law, 1 over 4 pi epsilon naught r square, 1 over 4 pi epsilon naught r square in the direction of r hat. Now then, I need to add all the dq's here. So the summation becomes an integration. Now it becomes a volume integral. So this volume integral means it's a triple integral. This surface integral means it's a double integral. So in summary, so if it's a line charge, then you have to apply this formula. If it's a surface charge, then you have to apply this formula. It's a surface integral. If it's a volume charge, then you have to apply the volume integral. And just to recap, this table summarizes the line element, the surface element and the volume element in Cartesian, cylindrical, and spherical coordinate systems. The line element that we saw was a vector. You can have it as a vector or a scalar that you see here, depending on the application.